In the next couple of lessons, we're going to have a look at Chapter 10 on trigonometry. We've already done Chapter 9 about the sine and cosine rule, but this chapter is a bit newer to you, not in GCSE really. We're going to look at some of the graphs of trig functions. We're going to look at solving trigonometric equations, and we're also going to look at something called trigonometric identities as well. Okay. Now, the first thing I wanted to show you is where the graphs of our trig functions actually come from. So I'm going to use this to show you. This is something called the unit circle that you'll see pop up quite a few times when we study trigonometry. So we've got a circle and it's got a radius of 1, hence why it's called a unit circle. And what I can do is within this circle I can draw a triangle like this. Okay, so it's got a length 1 on the hypotenuse, and then it's got two sides. It's got a cos side and a sine side. And the reason why they're sine and cos is think about your right angled triangle geometry. Opposite the angle, so this is the angle in here, I can change. At the moment it's 48, I can make it less than that, I can make it more than that. We can go right around the circle like this. Okay. Now, if we leave it on 48, this side here is opposite the angle, and we know the hypotenuse is 1. So that is 1 times sine of the angle. So the length of this red dashed line here is 1 sine theta, or just sine theta. In this case, it would be sine 48, would be that length. Here we've got the adjacent side, so this is going to be 1 cos theta, or in this case, it's going to be just 1 cos 48. So no matter where we put this triangle, so no matter what angle we put it at, so if I put it over here, the length is still going to be sine theta, because it's still opposite, and the other length is still going to be cos theta, because it's still adjacent. Now, as you can see, as we go around the circle, so if we just look at the vertical part, so the sine part, when theta is 0, or close to 0, it's very, very small. As we increase the angle, it gets longer and longer and longer until its maximum length is about here at 90 degrees. And then it gets smaller and smaller and smaller again. When it's down here, it's below the axis, and actually it would come out to be a negative number because it's below the axis. Okay. Now let's think about what happens with cosine. So we're now looking at the horizontal length on the bottom. That actually starts at its longest length at 0 degrees, because it's the width of the circle. As I increase the angle, cos actually gets smaller until at 90 degrees when it's actually 0. And then again, it gets bigger, but actually it's going to be getting more negative because it's towards the left, until it gets to a maximum again about 180. And then it gets smaller again. And we can use this idea to generate the graphs of sine, cos, and tan. So this is basically doing the same thing. It's just got a nice picture of it. I think that's the London Eye there. Now if I increase the angle, and what I'm doing is I'm plotting the length of the vertical, because that's going to give me sine of the angle. Okay, so when it was 0, it started down here. Now that it's at 60 degrees, its length is this, which is going to be sine 60. You keep going up at 90, it's got a length 1, which is its maximum. And then it starts reducing again. Once we get to 180 degrees, it's now 0, because the vertical height of that triangle is 0. And if we keep going, then we're actually going to get a negative length because it's below the axis. And so that's what gives our graph this negative portion. Okay, then when we get back to 360, it's a length 0 again. And that's the graph of y equals sine x. We're going to do the same process for cosine. So this time, we're going to look at the horizontal bit of my triangle. So here, we're actually going to start at 1. We're going to start here because this length is 1. As I increase the angle, that length actually reduces until when you get to 90 degrees, it's 0, because there isn't any width to my triangle anymore. Can keep going, and it's now going to be negative because it's on the left of the axis. Keep going. Again, it's going to be a maximum again at 180, so it's going to be -1 because it's 1 unit to the left. Then we can keep going around. Okay, there we go. So that's where we get our cosine graph from, which looks like that between 0 and 360. The graph for tan is slightly more complicated, but I'll show you what our interpretation is of the tangent, and you'll see now why it is called the tangent function. What I'm plotting is the length here. Okay, so you can see there's a tangent drawn here at Q, and I'm plotting the length of that. So it's basically if my angle is 67.5 and I just drew a line from the center to that tangent, how long does that tangent need to be? So when the angle is quite shallow, that tangent doesn't need to be very long. As the angle gets bigger and bigger and bigger, the tangent has to extend outwards. Once it gets close to 90, because that line's going to be vertical, they're not actually going to intersect. So you don't get a solution at 90. As we then go to more than 90, the tangent is now actually down here somewhere. And this blue line cuts through the circle and then reaches all the way down here to the tangent line. So it starts off very negative and then comes back towards 0. At 180, it's then 0 again. And then we get the same pattern repeating from there. Okay. Tan x is probably the hardest one to think about, but as long as you know the graph, that is the important bit. But that's where it comes from, is this idea of a tangent on the edge of the circle, and how long does that tangent need to be to intersect this line. And there we go, that's what the tangent graph looks like. These dashed lines where we don't have any values, so at 90 degrees because it's vertical, that doesn't intersect the tangent at all. So here that you can see where they cross at the point Q. At 90 degrees, they then don't intersect, so we don't get a solution at 90. And we also don't get a solution at 270. So on our graph, this dashed line is called an asymptote, which I think we talked about before when we studied graphs earlier in the year. So let's just summarize those 3 graphs. Okay, what you need to be able to do is sketch them. Okay, it doesn't need to be perfect, your sketch, you just need to have the key shape and the key points on there. So if I'm drawing sine x, this is what I would draw between 0 and 360 degrees. Draw my axis like this. It starts at 0. We get a curve that looks like that. It obviously keeps going past 360 as well, but that is what it looks like between 0 and 360. Okay, and the maximum height is 1. The minimum height is -1. This point would be 90, and this point would be 270. Okay, and just also understand that it does repeat in this direction and it repeats in the other direction as well. In fact, if I show you that on here, so if we draw on here sine x, okay, there you go, and you can see that it repeats in either direction as far as you like. Okay. If we're drawing the graph of cos x, I'm going to use the same axis, just between 0 and 360. But this time we observe that when we use the unit circle, it started at 1. So the graph of cos x looks like this. This is 90, and this is 270. And it's got a maximum of 1 and a minimum of -1. For the graph of tan, we had those 2 asymptotes, and those are probably the easiest things to label on here. So we had an asymptote at 90, put that on first, and we had an asymptote at 270, so put that on as well. Okay, and then those can help you draw the graph. So started at 0, then increased like this. In the middle, we had this shape, where that point at 0 was 180. And then down here, We had that shape. And what's happening on tan is this shape in the middle is basically repeating itself, because actually this continues down here and this continues up here. So it's that sort of pattern in the middle that's repeating itself. Now let's think about how we can use these graphs to solve some equations and use these graphs to help us. So find the solutions of the equation sine theta equals a half in the interval 0 to 360. So let's just sketch the graph between 0 to 360 again. Okay, so there's 0, 180, 360 equals a half. So we're drawing a line on at y equals a half and seeing where they intersect. So there's one solution here and there's one solution here. To find your first one, you can use your calculator. So you can do inverse sine of 1/2 to give me theta, which would give me 30 degrees. So that's the first answer here. That's what this would read off on the graph, 30. Now looking at the graph, it is symmetrical about 180. So this one here is going to be the same gap between 0 and 30 as it is between 180 and this number here. So to find this other solution, I can do 180 minus 30, which is 150 degrees for my other answer. I could even keep going further than that. Here we've been given the limits between 0 and 360, but in theory, this graph keeps going. So there is another solution here and another solution here. Now to find those two, because the graph of sine repeats itself every 360 degrees, I can take this solution and add on 360 to get to this one. Or I can take this solution and add on 360 to get to this one. And I could keep doing that to find all the different solutions and all the different periods of sine. Okay, this next one. Solve between 0 and 360, 5 sine x equals minus 2. So sine x would be minus 2 over 5. Sketch the graph. Minus 2 over 5 might be down here-ish. Two solutions. So the first one, if we do inverse sine of minus 2/5, and I get minus 23.5. Now that doesn't seem like the answer according to my graph, because this answer looks like it's more than 180. So how do we do with that? Well, what we've actually found is an answer down here somewhere, because the graph, remember, keeps going in this direction. So what we've just found is that answer there. Okay. So how could we go to the next solution? Well, this is minus 23.5. We said that the graph was periodic with 360 degrees. So it repeats itself every 360 degrees. So what I'm going to do is I'm going to do 360 plus 23.5. So that gives me 383.5 degrees. Oh wait, sorry, plus minus 23.5. Let's just correct that. So I've got minus 23.5 because I'm adding on that number, which gives me 336.5 degrees. So that would be this answer in here. Okay. The other way that we came up with a solution before was by doing 180 minus our answer. And that will actually work here as well, because this gap here is going to be the same as this gap here. So I can do 180 minus 23.5. So 180 plus 23.5, because the gap is going to be the same using the symmetry of the graph. So that's going to give me 203.5 degrees, which is that one in there. Okay. So with sine, to find multiple solutions, we can do 180 minus our answer, because think about the symmetry of the graph in these gaps, or we can do 360 plus our answer to find the solution on basically the next wave later on. Okay, let's have a look at cos. And we've got cos x equals root 3 over 2, so let's just put that on. So I'm going to get two solutions between 0 and 360. So I need to do inverse cos of root 3 over 2, which is 30. So that's going to be my first solution here, 30 degrees. To find my other solution, I need to think about the symmetry of the graph again. Well, cos is symmetrical about 360. So this gap here is the same as this gap here. So that's going to be 30 degrees as well. So to find my last solution here, I can do 360 minus 30, which is 330 degrees. So those are my two answers there. Again, like sine, this graph repeats itself every 360 degrees. So this would be my graph up to 720. So if I wanted to find two more solutions, I could take those two that I just found and I could add on 360 again. So for cosine, we can either do 360 minus your answer or 360 plus your answer to find the ones that are on the next period of the graph. Let's have a look at a tan one. I'm going to do this one here, G. So that'll give me tan theta is minus 11 over 3. Let's think about what the tan graph looks like. Now minus 11 over 3, that's somewhere down here. So it looks like we're going to get two solutions between 0 and 360. So to find theta, I'm going to do inverse tan of minus 11 over 3, which gives me minus 74.7. Now again, that's not on our graph, that's going to be down here somewhere. Okay, presumably it's this solution here. So to find the next one, tan is actually really easy because the whole graph just repeats itself every 180 degrees. Because look, at 0, I get that shape, then at 180 I get that shape, and then at 360 I'll get that shape as well. So tan just repeats itself every 180. So all I need to do is just add on 180 to find the next solution, which gives me 105.3. Okay, so that's going to give me this first one here, and then to find the next one I can add on 180 again. 285.3. So those would be my two solutions here. I wouldn't want the minus one just because the interval is between between 0 and 360. So for tan, to find multiple solutions, we just add on 180. Simple as that. So let's just summarize what we found. I'm going to just draw on some examples. Maybe I'll just put on about 1/2. So if I just put on a line at y equals 1/2, so perhaps we're solving each of these equations equals 1/2. So for sine, once we've got the first solution, we can find the next one by doing 180 minus that. Okay, so we can do 180 minus our answer. To find these next two, we can take those two answers and we can do them add 360 because they are a whole cycle later. Okay, there's 360, and this just repeats itself every 360. Okay. For cosine, let's draw the same thing. Let's just draw a line going across. Now the first solution is here. The second one is here. And what I want you to focus on this time is the symmetry around 360. So this gap here is the same as this gap here. So to find our multiple solutions for cos, we can do 360 minus our answer. And if we want to find the solutions further up, so for example this one, I could do the first one plus 360 because the whole graph repeats every 360 degrees. For tan, so my first solution is here, my second solution is here, my third solution will be about there, and the graph goes back up. All I have to do here is add 180, because the whole graph repeats every 180 degrees. You could say it has a period of 180 degrees, whereas the other two have a period of 360 degrees. Okay. One other thing I want to look at is trigonometric identities. So I've got the unit circle here again. I'm just going to label some things on it. So this has got length 1. This is going to be angle theta, which means that this would be cos theta, and this would be sine theta. Now using this unit circle plus some trigonometry we know already, we can get some identities or some facts or formulae that are always true. I suppose they're not technically formulae, but they are technically identities. I'll explain more about that in a minute. If I use Pythagoras on this triangle, because it is a right angled triangle, then this side here squared plus this side here squared should make this one here squared. So sine theta squared plus cosine theta squared should equal 1 squared because it's a right angled triangle. Now when we write sine theta squared, we tend to actually write it as sine squared theta. It's just a bit of notation for how we write it. Cos theta squared is cos squared theta, and 1 squared is obviously 1. Now because this holds true for any value of theta that I can put in, it is called an identity, so something that always is true. And we can use a triple equals sign for an identity. And that's the first trigonometric identity. I'm going to talk about how we can use these later on, but that's the first one. You say sine squared plus cos squared equals 1. Okay. Another one we can use is using the tangent. We know that tan theta is the opposite divided by the adjacent. So in our case, tan theta is equal to the opposite, which is sine theta, divided by cos theta. And that's another identity that's always true for any value of theta. So actually we can put a triple equals in here. Okay, so we've got two identities. Sine squared plus cos squared is 1, and tan theta equals sine theta over cos theta. And we're going to be using those in the next couple of lessons to help us solve some more complicated equations as well. Okay, let's have a look at a couple. So this equation is different to the last ones we did because we've now got sine and cos involved. Let's just start by writing the original equation. I can't solve this straight away because how do I know whether to do inverse sine or inverse cos? So I need to do a little bit of rearranging first. So I'm going to divide both sides by cos theta. And now, using our identities, we know that sine theta over cos theta is tan theta. And now this is a problem that we can solve. And we've got to solve it between 0 and 360. So I'm going to draw my tan graph between 0 and 360. And we're solving where it equals root 3. So we're going to get two solutions. So theta, so I've got to do inverse tan of root 3, which is 60. And to find the next one, I can just add on 180. So that's 240. There we go. Let's get another one. Okay, solve this equation between 0 and 360. Again, we've got sine and cos. So let's move the cos to one side. Going to move that onto the right-hand side. Okay. And now I could divide both sides by cos theta. So this left-hand side now is going to become 2 tan theta equals 3. So then tan theta is 3 over 2. And then I can solve this as I would normally. So inverse tan 3 over 2. My first solution is 56.3. My next one, add on 180, 236.3. And those would be my solutions there. So we can use these identities to help us. All right, this looks a bit more complicated. 4 sine squared x minus 3 cos squared x equals 2. And we've got to rewrite it as this. Okay, at least this will show that question so we know what we're aiming for. So we don't want this cos squared in there. We want to try and get rid of cos squared. So what we can do is we can use the other identity we had before, which was sine squared x or theta or whatever your constant is equals 1. So if I want to get rid of cos squared, I can rewrite this as cos squared x is 1 minus sine squared x. So now when I rewrite this equation, I can rewrite it as 4 sine squared x minus 3 times, then instead of cos squared, I can write 1 minus sine squared x. And this is useful because I've now changed this equation to just having one type of function in it, just like I did in the last one. Now I've just got to simplify it. So I've now got 7 sine squared x equals 5. And that was what the question asked you to show. And it says, hence, solve this equation between 0 and 360. And this equation is the same as the one in the first part. And we've already shown that we can rewrite it as this. So it's basically solve this equation here. So sine squared x is 5/7. So that must mean when I square root both sides, sine x is going to be plus or minus root 5 over root 7. I'm just going to write it as square root of 5 over 7. Now we've got two answers here, so we're going to have a fair number of solutions between 0 and 360. There's the curve. Here's the line for positive square root 5/7, and here's the line for negative square root of 5/7. So we're going to have 1, 2, 3, 4 different solutions. Let's try and work them out then. So let's deal with the positive ones first. So inverse sine of the square root of 5/7. That gives me 57.6. So that's this first solution here. To find the next one, I'm going to do 180 minus that. So it gives me 122.3. Now we'll deal with the negative ones. So I'm going to do inverse sine of minus root 5 over 7. And that's giving me minus 57.6. I'm just going to write that down. That's not a solution for us because we want them between 0 and 360, but let's apply the rules. Let's do 180 minus that answer. So that gives me 237.6, actually 0.7. The other rule we had was to do 360 plus that answer. So I'm going to do 360 plus minus 57.6, which gives me 302.4. Okay, so I don't really need this one because that's outside my range. But there are my 4 solutions. Okay, to practice solving some equations that look like this, and practice solving some equations where you have to use an identity first as well, have a look at exercise 10D in the book. If you want some extra questions as well, you can have a look at section 10.4 in the practice book as well, because I find that students quite like to have just lots of questions to practice this skill.